I'd like to review the answers to Quick Check 6.1. So we'll start off here, exothermic and endothermic. So for each of these little ideas, we should be able to talk about whether it's exothermic or endothermic. So Q is greater than 0. The heat is being a positive number. Positive means that it is taking energy in, so that's endo. Okay, heat is released. That's the definition of exo. Okay, molecular attractions are strengthened. Okay, if they're strengthened, that doesn't make sense to me. If they're broken, that's going to require heat. So if they're strengthened, that's going to give off heat. So this is exo. But I think about it in the other direction. Again, here's a reaction that's giving off heat. If it releases heat, that's exo. Okay, to the right, Q is less than 0. Okay, well, Q, that's a negative value. Negative value is always exo. Okay, bonds are formed. Okay, when you break bonds, that requires energy to break things. But if they're formed, then it gives off energy. So this is exo. Heat on the left side, okay, that's taking heat in, so that's endo. And heat is absorbed, same thing, this is endo. So these are a little bit tricky, you have to kind of think about them. Okay, draw the potential energy graph. If heat's on the left, that means heat is absorbed, so wherever we start, if it absorbs heat, it's going to end up higher. So that's going to be an uphill graph. And the same thing here, if heat's on the right, the heat is given off, well, wherever you start, if heat is given off, that means you're going to end up at lower energy. Now again, these we're talking about potential energy, not kinetic energy. And somebody might say, well, if heat's given off, isn't everything getting hotter? Well, the surroundings are getting hotter, but we're talking about the chemicals in the system, and the chemicals in the system must be getting lower in energy in order to release some energy. Now the last part about the Q being positive or negative, okay, we always take the final value minus the initial value. So in this case, we take a low number minus a high number. So in this case, Q would be a negative value, less than 1. And here we're going to take a high number minus a low number. So that's going to be Q is a positive value, greater than 1. Okay, now this is a kind of a general problem, and the idea, it's not a calculation. So remember, specific heat is how much a material resists change in temperature. Resists change in temperature. So that's important, that's the key idea. So you have two blocks, okay, they have the same mass, and they're both going from 20 to 50. So the idea is for X, this takes 100 calories to change. Okay, this one takes 400 calories. So the idea is if it takes 400 calories, which one is resisting change more? Well, obviously this one is, because you had to put 400 calories of energy in to get it to change 30 degrees. So Y is has a greater specific heat. And why? Because it resists change greater. Yeah, that's bad. It resists change, that's a C. Resists change more. So the more it resists change, the greater the specific heat. Now we do get some calculations. Okay, show your work. Calculate the value of Q, so we're looking for Q, when a 35-gram piece of glass, so 35 grams, cools from 128 to 85, and C is given 0.84 joules per gram degree. And all I have to do is do my math here, so 128 minus 85. So that's a 3 and that's a 4, so 43 degrees Celsius. So Q equals MC delta T, so we're going to substitute. So 35 grams times 0.84 joules per gram degree times 43 degrees. I'm too close to the edge. And I'm going to get my calculator. Okay, from my calculator I get 1264.2 joules because my, I can't read my writing, grams drops out, degrees drops out. But this is only really good to two significant figures, so I'm going to round that off to 1300 joules. So that's the value of Q when it cools. Now, when it cools, okay, this is going to actually give off energy. So the value of this really is negative 1300. And the reason that I should have known that was because when I up here did my math, I did it wrong. The idea is it's always the final minus the initial. If it's cooling down, then it is the final is 85 degrees, and I would subtract 128 degrees, so I'd have negative 43 degrees as my delta T. So this should be negative, and that would make my answer here negative. So I know that if it's cooling down and releasing energy, it should be negative, and I can see why in my math. Okay, another similar question. What is the mass of a block of lead if 500 joules of energy, so that's our energy, is required to increase the temperature from 50 degrees to 110, so final minus initial is going to be 60, positive 60 degrees, and C is 0.129 joules per gram degree, and then obviously I'm going to look for my mass. So I like to take this and move my equation around so that it equals mass. So mass is equal to Q divided by C and delta T. Q is 500 joules divided by 0.129 joules per gram degree and 60 degrees. So degrees drops out, joules are going to drop out, grams on the bottom is going to end up on top. So do my calculation. So I'm getting 64.599 grams. And my significant figures, it's kind of hard to say. It looks like this is only like one significant figure, but we'll go ahead and call this 65 grams. That's really sloppy. Let me try that again. So the mass of my block is 65 grams. Okay, last one here. This one we're given the energy in the equation. Okay, so that would sort of be our delta H. And what we're saying, we're going to use that as a conversion factor. So for every mole of reaction as written, it's going to release 112 kilojoules of energy. So I want to know how many grams of NO were recreated if 45 kilojoules of energy was released. So 45 kilojoules. Now, we don't have to say negative 45 kilojoules because it says the word released, so that takes place with a negative sign. So that many, and I know I get 112 kilojoules for every mole of reaction. And every time this reaction goes, every time I have 1 mole of reaction, then I can see I'm going to have 2 moles of NO, and 1 mole of NO has a certain mass, and my masses are going to be 14.01 for nitrogen. Oxygen we know is about 16.00. So it looks like 30.01. And now all I have to do is calculate. And I'm getting 24.11 grams of NO. And looking at the problem, it looks like I have 3 significant figures. So I'd round that off to 24.1 grams of NO. So this is a similar problem like we were doing, in earlier units, and it's just that I'm using my 112 kilojoules as a conversion, 112 kilojoules for every mole of reaction. Then I have my mole ratio, and I have my molar mass, And the rest of this seems pretty familiar. That's the answer. That's done.